This video is for AP Calculus, Chapter 7, Lesson number 3, box number 3. And the notes actually begin here. I guess it would be page 14. Not very many notes actually for today's lesson, only 4 pages. But just before we actually go and take a look at those notes, I just want to go back and just kind of quickly look at some of the things we were doing on the day before. This was actually kind of an old problem to us. We were using kind of a rectangular approximation method in order to come up with the answer for that. But really we were applying the idea of using integrals to accumulate some sort of story, to accumulate a rate, to find an amount. Some of them were a little more technical. Let's go back a couple. There was this one here where we were adding up little chunks of an overall slab of metal, trying to figure out what the total mass would be. And our plan was to add up a whole bunch of little masses in order to find the total mass. Once we found a nice little symmetric way to cut it up, then it actually wasn't too bad. Probably our most technical one was this one, where we were taking a look at trying to find the overall amount of flow out of a pipe. And we had to first kind of look for some symmetry, and we found out that the little onion rings worked really well. And then we just added up a whole bunch of little flows in order to find the total flow. Today, the stuff that we're going to do today is kind of old news to you, but we're going to look at it in a slightly new way. So it's kind of a good thing, right? Nice little gentle start here. It says analytically, so by hand, see if you can find the area under the curves but above the x-axis. So I just want to sketch these out. You could, of course, use a graphing calculator if you wanted to, but I don't think these are too bad. A parabola there, it's going to go through the origin. It's going to go through 1, 1. Probably going to go something kind of like that. And then y equals 2 minus x. I'm going to throw some color in here. Would have had a y-intercept of 2. It's going to hit that point 1, 1. And then it's going to hit the x-axis there at x equals 2. And it also says, hey, we're finding the area that's above the x-axis. So there's another little boundary line here, right? So we're kind of now able to see that kind of weird little shaped wedge in there that's above the red line, but below the blue and below the green. And we have to try to find the total amount of area that's in there. So one of the things that makes this question interesting is we're going to have to do it in a couple of chunks. A couple of little sections in order to get it to work. We're going to add up some little ribbons in here, right? So we've got some ribbons in there that have some, dA to them. And then there are going to be some ribbons over here that also have some small little amounts of area to them. Now I'm just going to go over to the side of the page here for a second and just kind of think of a general plan. Generally speaking, we've got some top, some second function sitting up above some other function. This function on the bottom might be as simple as the x-axis, but we've got kind of a ceiling and a floor, and then we're trying to look at little rectangles of area that form in between the ceiling and the floor, right? So if we think about those rectangles in terms of how tall they are, their height there, if you were to measure their height, it's just y2 minus y1. Now, their thickness going across is actually going to be some small little change in the x value as you work your way along the x-axis. So we would call that dx. So a couple little issues here. There is a difference between x and dx. X just tells you where you are. It tells you, hey, x is the address of this little ribbon of area, and then dx is actually how wide that little ribbon is. Okay. Kind of got my plan ready to go here now. I'm just going to think about this in nice simple terms. The total amount of area is actually just going to be the sum of little ribbons. Okay, so really what I'm going to be doing is just summing up some dAs. All I have to do is teach the calculus how to find out what those dAs are. Pretty simple, just length times width, and we're good to go. Yeah, there is an issue where we have to do this question twice, once under the blue and then once under the green, but that's not too bad. So the area here in this story, let's do the blue part first. We're going to be integrating. All I want to do is just tell it about the dA, right? So I'm just looking at this and saying, okay, there's some area here, and we have to go and tell the calculus how to find that area. So the height will be the difference in the two functions. Sometimes that's the x-axis for one of them, and then the width will be dx. So I'm going to have here a height of x squared minus 0 for the x-axis. I could put another function in there if I wanted to make a more interesting question. And then I'll multiply that by dx. So there, I've just taught calculus how to find a little dA. Now, x is in charge. I can see that because of the dx. So I can now look and go, okay, where does the first ribbon start? Well, that would be at 0. And then where does that last ribbon end? That would be at 1. So this is going to be an integral from 0 to 1. And then I finish it off doing the other section here. So we'll be underneath that one function, 2 minus x, and then subtract 0. If you desire to put some extra brackets in just to kind of get a feeling for that, that's okay. Yeah, you can do that. And then dx is how wide it is. That one would be from 1 to 2. There. The whole focus of this chapter is up to that point, just getting the integral set up. Beyond that, it's actually back to the previous chapter doing some antiderivatives. But this chapter is all about getting comfortable setting up those integrals. So now it's just some math. We're going to go and do some antiderivatives. The antiderivative of x squared, well, that's going to be like an x cubed, a little bodyguard here, a little 1/3. Yeah, and we'll evaluate 0 and 1. And then we'll also do this other one here. So this is just, well, it's just 2 minus x. If we do an antiderivative on the 2, we'll get 2x. And then an antiderivative on the x, we'll have a minus 1/2 for a bodyguard, and then x squared. Okay, little evaluation here. We're going to evaluate at 1 and 2, and we always go final minus initial. This thing's pretty much done. It's technically not where you could leave it for AP because you can't just say, oh yeah, put that into my scientific calculator. You'd have to do at least one more step where you go and throw the numbers in. But they're pretty easy numbers, right? Putting in the 1, we're going to have 1/3. Putting in the 0, okay, minus the 0. And then moving on down the road, putting in the 2. 2 times 2 is a 4. And then a 2 going in here. Okay, well, I'm going to have 2 squared is a 4. Take half of that. It's 4, take away 2. There, that's what happens when you put the 2 in. And now we'll go and put the 1 in. 2 times 1 is 2. And 1 squared is a 1, minus a half. Okay, pretty much done. I mean, now we're just cleaning it up, and maybe it's better even just to leave it as it is. I don't know. We've got a 1/3. What do we have here? Plus 2, and then minus a 2, and then plus a half. Okay, the 2's go away. Really, it's just a 1/3 and a half. So what is that? That's like 2/6 and 3/6. Hey, we're done. 5/6. There, we did it analytically, did it by hand, and we found the area there. Again, the key thing for this chapter is not so much the integrals. It's actually everything just up to setting it up. This chapter is really all about that. Looking at the picture going, oh, I can tell the calculus how to do one little incremental tiny thing, and then I'll let it go and add them all up. So here we're just adding up those little ribbons. Okay, let's try another one out. This one I'm noticing it says, oh, we're going to do this numerically. So yeah, we're going to need our graphing calculator for that, probably because of that weird function, √5 minus x. Okay, well, drawing this out, the first one looks just like before, just a little parabola here, no big deal. And then √5 minus x, well, it's going to have a slightly different y-intercept than the one a moment ago. It's going to be a little bit higher, and it's going to have a different x-intercept as well. So it ends up looking, I don't know, something roughly like that. Kind of awkward and irrational. And we're still above the x-axis, so we still have this line down here on the bottom as our floor. Okay, yeah, I'm going to use my graphing calculator. I'm going to need to locate these values for where we transition from blue to green. So right here, maybe I'll just call that capital A, and then this value here, B, which yeah, if you're observant, you might even already know what that is. But I'm going to do this on my calculator and just see what happens here. So I'll turn this all on. Okay, clear those out. So I've got y equals x squared, and then the other one is a √5 minus an x. My zoom, I might as well kind of match the window that we have here. I don't know, maybe from 0 out to about 3, and the y's 0 up to about 2 is probably fine. Yeah, okay, great. So yeah, I'm going to ask my calculator what these values for A and B are, so I can calculate. I'm going to do an intersection and the two curves. Yeah. Okay, so that intersection is at around 1.0767. It's probably right now stored in X, so I'm just going to quit out of here for a minute, take a look. Yeah, there it is. I'm going to store that as A because I know my calculator likes to use that. So this A value is somewhere around 1.07672, but I'll grab the precise number when I go to do this. Now the other value I'm going to need is that x-intercept. It's actually just going to be root 5, but if you weren't sure, you could go calculate. I need a 0. I need to know where this thing is going to touch down, not for that curve, but for the second one. So I can do a left bound, yeah, somewhere in there, and then a right bound. I'll just go past it and then let it guess. And it's going to come up with, as it did, just the square root of 5. Okay, so I'm going to quit out of here for a minute and then go, okay, x value, are you there? Yeah, there it is. There's the root of 5. So I'll just go store into B. Okay, I've got it. So I've got that value out here for B if I need it. 2.23606, otherwise known as the root of 5. Okay, fantastic. I'm still going to do the same game that we did before. Right, I'm just going to tell it how to do some tiny little rectangles that are in there. So I've got, a rectangle here under the blue but above the red. The rectangle's width is dx, but its location is at x. And then there'll be rectangles out here as well. I'll just have to add them up. So I'm just going to tell my calculator or my calculus, hey, calculus, you need to go and integrate some dAs. In fact, you're going to have to do it twice. Right? There are 2 sections to this graph. Okay, so here goes. This next line is the reason why we're doing this chapter. So I'm going to integrate. Okay, this first little orange ribbon here, blue on top, red on the bottom. So I would be going root x and then minus 0, red on the bottom. Okay, and then dx. Oh, looks like x's are in charge. We're going to start at 0, and we're going to finish at this capital A. Okay, not like the A for area that I've got there, but this value right there. And then we're going to do another one. We're going to say, wait, there's more area coming. We're going to integrate. This time it's green on top and red on the bottom. So, okay, green on the top. I've got this root 5 minus x, and then subtract 0. That's how wide, sorry, I should say how tall the rectangle is, and now here's how wide it is. It's dx wide. Oh, looks like x's are in charge. We'll start at location A, and we'll finish at location B. And now at this point, I would literally just throw that into my calculator. I would let my calculator have just constant A and constant B. You can try it out. I don't want to bore you with that here online. I'm just going to tell you if you want to check it. And you should have it to 4 decimal places. It's 1.0881. And just let your calculator do that numerical integration. Okay, so that's halfway through the day. Those are actually old questions. You've already seen those. But I wanted to do them again to just kind of have a bit of a baseline for the 2 that we're going to do today. Okay, so we're going to do 2 more questions. We're going to do this one here. So this is titled Areas Between Curves but with Interesting Boundaries. Okay, so there's that square root of x and then an x minus 2. We're going to do that one. And then if you look at the next example, we're going to do the exact same thing again. We're going to do this question twice. Both times we're going to come up with the same answer, which is 10/3, right? There's no secrets here. But I want to show you 2 different ways to do it. So this first time, we're going to be doing an integral with respect to the x-axis. This is what you guys already know. Okay, this is nothing new to you. But then on the second time we do it, I want to show you a slightly faster, more impressive way to do this. I still have this, blue on the top here. And I've got my x-axis down below. But then the floor changes, right? The floor, it's not always the x-axis. At some point it becomes this slanted line, x minus 2. Okay, well, thinking about the story I'm going to give to the calculus, I'm going to say, hey, calculus, you're going to have to add up some little ribbons in here. Blue on top of red. Oh, but wait, after x equals 2, it's going to be blue on top of green. And I'll just tell it about that, and then we're good to go. So the area. The area is really nothing more than a sum of little ribbons. That's all we're doing. We're just adding up some DAs. We'll have to do it in 2 sections until we get to the second example. But this should work fine. So okay, here we go. Going to integrate. At the beginning, it's blue on top of red. So I'm going to have root x. I just realized I made a mistake earlier, I think. So I'm going to stop here for a second. You might have been wondering what was going on in the previous example. I think I was looking at the wrong section of notes. Yes. Okay, I apologize. You probably were wondering about this. Of course, that was an x squared graph. And down here, I should not have said root x. My apologies. At least it's fixed now. X squared minus 0. Okay, but this one is actually root x. So apologies, I was looking at the wrong one there. Root x minus 0 and a little dx for how wide it is. Oh, x's are in charge. Looks like for that we're going to integrate from 0 to the place where we switch from red on the bottom to green on the bottom. So that's at 2. And then one more of these. We're going to be integrating again another little orange ribbon there, blue on top. So that's going to be a root x on the top, but this time a green on the bottom. And here you have to be careful. You probably, while you do need to have some brackets, I can't just say minus x minus 2 because it needs to say minus x minus 2, right? Because that's the one function. This whole function here is x minus 2. All right, that's how tall it is. Dx is how wide it is. Looks like we'll begin that process at 2 and we'll finish it at 4. Okay, well, we can do this any way we want. We could do it numerically because it didn't say not to. It didn't say do it analytically. Or we can try to do it analytically. You could do it either way. Let's give it a shot. So this is like x to the 1/2. If I integrate, I'm going to have x to the 3/2. Oh, but I need a bodyguard. How about a 2/3? And then we'll evaluate that at 0 and at 2. And then another one of these. Okay, well, that's the same antiderivative. That's going to be 2/3 for a bodyguard, x to the 3/2. And then I'm going to have minus a 1/2 as a bodyguard, x squared. And then we're going to have a double negative in there, so plus a 2x. That's the antiderivative. And then we'll evaluate it beginning at 2, finishing at 4, and then we'll go final minus initial as always. Throw the numbers in. What do we have here? 2 goes in. It looks like we're going to be cubing it. That'll be an 8, and then rooting it. So there's a root 8. So this is like a 2/3 root 8. Don't worry, it's going to go away in a second anyways. Then we're going to put the 0 in and get nothing. Okay, so minus 0. Easy. Now going down the road, putting the 4 in. 4 goes in. You can square root or cube in either order. So I'm going to square root first. 4 square rooted is a 2. Cubed is an 8. So this is like 2/3 times 8. Still putting the 4 in. 4 squared is 16. Cut that in half. So minus an 8. And then 2 times 4 is plus an 8. Ooh, those are going to go away. and then subtract. Now we'll put the 2 in. So we put the 2 in, and you're going to be rooting an 8. So there's going to be a minus a 2/3 root 8. No problem. Already saw one of those. They're going to go away. And then the last two terms, 2 squared is a 4. We cut that in half, so minus a 2. And then 2 times 2 is a 4. Okay, so some of this goes away, which is quite nice. We've got minus an 8 plus an 8. You're gone. And then this weird root thing, that's gone too. So when it's all said and done, there's not too much left. It's good because I don't have much space left. What do we have here? 16/3. Minus a 2 plus 4. Okay, so that's like plus 2. So 16/3 plus, oh, sorry, I got a negative issue going on here. Minus sign on that. This should have been a minus and a minus. So 16/3 minus, what would be 6/3? We're done. 10/3. Okay. A couple little hiccups there, but we managed to get it to work. We're going to do the same example again, and then the lesson's done. But I want to show you a more interesting way. It'll bother you a little bit at the beginning because it's not what you know. But once you get comfortable with the idea, it can actually be really powerful. So at this point, we've got 2 separate integrals that we did. We're just adding up those little orange ribbons. At the beginning, blue on top of red. Then we had to switch to blue on top of green. Same question again, same answer, of course, 10/3. But this time, we're going to do an integral with respect to y. It won't feel particularly comfortable for you, but it is kind of neat to see. So for this story, the plan is, instead of thinking about it as being like the old way, so here's the old way over here, you know, you've got some y2 sitting on top of some y1, and then we had our ribbons going like this. And the height of the ribbon was just y2 minus y1. And the width of the ribbon, for how wide it is, that was dx. Okay, whole new game plan. What if we wanted to do this all in one shot? What if we put in little ribbons that looked like this and worked our way up the page instead of over the page? And we could say, oh yeah, these are little horizontal ribbons that reach from left to right. Okay, so that's a slightly different story here now. So let's kind of draw this out. We've got like one function doing that and another function kind of doing this. Okay, it doesn't really matter which function we want to call which. Maybe I'll call this first one just as you work your way across the x-axis here. This one's got the first set of x values, and then the green one, I'll say that's like x2, the second set of x values. And then this little ribbon we're going to do just reaches from left to right. It'll feel a little bit awkward because you're so accustomed to thinking of functions as being functions of x, but now they're going to be functions of y. The height of this really small little horizontal strip is going to be dy, and it'll be located at y. So y will decide what ribbon we're on, what little horizontal ribbon we're on, and dy is how tall it is. Okay, here goes. Let's give this a try. So the area is going to be an integral, and now it's going to be a width times a height. Instead of the other way around. We used to do heights times widths. So this is going to be an integral where we actually take some second x value and subtract off some first x value. And then we'll go dy, and y's will be in charge. So we'll have like y equals our first y, and y equals our second y here. It's actually going to be really nice because it'll go really fast. It's going to give us a nice, quick, clean answer. But there is a cost, there is a catch. If you want to do this, and we're going to see this for the next couple of days as we finish up the main AP stuff, is that you have to invert the functions. So of course this will only work if they're functions that are one-to-one, and we can go ahead and invert them. These ones are. All right, so my first function there, I'm going to say that it's the square root one. Okay, so y1 was square root of x1. But I can invert that and say, hey, if I want to think about the x's as being a function of y, I just have to solve for x. So x1 is equal to y1 squared. Okay, actually, let's see if I can change the color on that without things messing up too much. That was the blue stuff. All right, now the green one on the end. For that one, y2 was equal to x2 minus 2. That's a function written in terms of x. You tell me what x is, I'll tell you what y is, right? That's the idea of that layout. But now let's rearrange it. Let's make it so it says, oh, you tell me the y, I'll tell you the x. So then that would say x2 is equal to y2 plus 2. So now we've got x's that are written in terms of y's. All right, here goes, and it'll be pretty quick. So the area, looking back up the page here, we're going to have to say the big X value minus the small x value. Okay, so the big X value is the one I have in green, it's the slanted line, and the small x value is the one in blue, it's more to the left. So we're going to have here, when we go the big minus the small, we're going to have to do y2 plus 2, and then subtract off the first x value. Subtract off y squared. Tidy this up here. We don't really need the subscript in here. Let me get rid of that. All right, and then dy is how tall it is. Oh, look, y is in charge. So we need to go and talk to y about where things begin and where things end. So for all these little orange ribbons, where do they first begin and where do they finally end? And now we're going to be working up the page instead of over the page. So thinking about these little orange ribbons, the lowest one would be down here at y equals 0. And then as you elevate up, the last one will be up here at y equals 2. Okay, so that tells me since y is in charge, that will integrate from there to there. So yes, there's a price to be paid. You had to invert the functions, but now it's one integral, and we can actually be done pretty fast. So I'm trying to find the antiderivative for that. It's not too bad to do. The y would be 1/2 y squared. The 2 would be a 2y, and then this is going to be like a y cubed with a 1/3. Little evaluation box, 0 and 2. And then we'll go final minus initial. So we really only have to put the 2 in, because when you put the 0 in, you get nothing. And so putting the values in, putting the 2 in, 2 squared is 4, half of that is a 2. Putting the 2 in here, we're going to have a 4. Putting the 2 in here, 2 cubed is 8, so minus 8/3. Hey, we're pretty much done. This looks like a 6 minus 8/3. That's going to be like 18/3 minus 8/3. 10/3. So of course it's the same answer. I think maybe the math on this one might have been a little bit nicer. And that can happen sometimes, where if you choose to integrate with respect to the other variable, you can actually get nicer stories. So we want to be open-minded, but yeah, there is a price to be paid. You have to, if you're going to do this, make sure you now have functions that are written in terms of y, not in terms of x's. So you do have to do that inversion of the function. And that's the end of the lesson for this third day in Chapter 7.